In chapters 11 and 13, we'll do some selected topics, and they'll be a little light on the calculations, as you might imagine. You can see your table of contents for those chapters here. We'll talk about some of that later. So we talk about the kinetic molecular description of liquids and solids. We talked about it for gases in the gas law chapter. But again, if we compare the strengths to interactions among particles and degree of ordering of particles, gases are pretty low because they more or less don't interact with one another for the most part. And liquids interact more, and solids are usually more rigid, and then therefore they have a high degree of interaction and a high degree of ordering. If two liquids are miscible, that means that they're mixable with one another generally in any proportions. Water dissolves in alcohol, alcohol dissolves in water. Gasoline dissolves in motor oil dissolves in gasoline. Either way, which one you consider a solvent is usually what's present in the larger amount. Immiscible liquids are not soluble in one another. If they're not soluble, whichever is less dense will float on top, whatever is more dense will be at the bottom. Water does not dissolve in oil. Oil floats on top. That's why when they have an oil spill, they can skim the oil off the surface of the water. Water does not dissolve in cyclohexane. Many of your organics are not water soluble. And that's why you don't see a whole lot of water in organic chemistry. A lot of times you try to avoid it. Now, there are four important attractions. One of those is ion-ion attractions, and they're just the attractive properties between two charged ions governed by Coulomb's law of electrostatic attractions. That's essentially what you have going on with an ionic bond. Now you can get hydrogen bonding. That is second in strength, but it's a particular case of number 3, which is the dipole-dipole attraction. You got polar molecules. The positive end of the molecules are attracted towards the negative ends, but these are particularly strong. You need hydrogen bonded to oxygen, nitrogen, or fluorine. For example, water is very polar. It can form up to 2 hydrogen bonds with other water molecules, which is why water is a liquid at room temperature. Ammonia and hydrogen fluoride are not liquids at room temperature. They're gases, but they have much higher boiling points than you would predict. That's because hydrogen bonding is a stronger force of interaction. You see this graph, group 6A, group 7A, group 8A, and compare that to group 4A, where no hydrogen bonding occurs. You see that they generally increase as a function of molar mass. More molar mass, higher temperature of boiling point, all factors being equal. But you see these with the lowest molar masses all of a sudden have much higher boiling points. Water at 100 degrees Celsius, which makes it liquid at room temperature, and therefore life as we know it can exist. But you can see they're all higher than you would predict, and that's because hydrogen bonding is a very strong force of interaction, even compared to other polar molecules. The other molecules would exhibit dipole-dipole interactions. It's just that. If BRF is a polar molecule, you've got a positive end, you got a negative end. The positives and the negatives attract. Like charges will repel, but you get a net force of attraction between the molecules. Now, London forces are actually very weak. They're actually the weakest force of interaction. They're present in all molecules, but they're the main force of interaction in nonpolar molecules. For example, if you got isolated argon atoms, as the argon atoms pass by one another, the electron clouds deform, forming instantaneous or momentary dipoles. And you do get a net attraction there, but it's a very weak force, very momentary, and that's why things generally go up as a function of molar mass. All other factors being equal, you got more stuff to deform in terms of electron clouds. But there can be some other influences like shape of the molecule or just how easily the electron clouds are deformed. And they call that polarizability. So which of these would exhibit, say, hydrogen bonding? Hydrogen bonding, the water and the HF both exhibit hydrogen bonding. Now what about our dipole-dipole interactions? That would look like our friend chloroform. You got 3 carbon-chlorine bonds, 1 carbon-hydrogen bond. All those bonds aren't the same, so that's going to end up with a polar molecule, and so you'd end up with a dipole-dipole attraction, albeit weak. What's left is our London dispersion forces, and that would be our friend propane. Carbon-carbon and carbon-hydrogen are London dispersion forces. And we'd find that all hydrocarbons just have London dispersion forces, and so you should get used to that result being the answer. But any nonpolar molecule, that's what you're going to put. Other properties like vapor pressure are dependent on these types of interactions. Vapor pressure is a equilibrium pressure of gas above the surface of the liquid. We talked about that a little bit in the gas law chapter. Increases as a function of temperature. If the intermolecular forces are stronger, however, the vapor pressure at a particular temperature will be lower. The boiling point of a liquid is related to the vapor pressure, and it's the temperature at which that vapor pressure is equal to the current atmospheric pressure, at which point the pressure pushing down the liquid can't hold it in the liquid phase. So you want to look for at what temperature does the vapor pressure equal the barometric pressure, and that's what you're going to work with. You can see that green line drawn at 1 atm. You can see diethyl ether has a pretty low boiling point because that happens at a low temperature. Methyl alcohol higher, benzene even higher, but water crosses here at 100. And so you can see that the boiling point is directly equal to the vapor pressure, which is related to the strength of the intermolecular interactions. So for example, if we had ethylene glycol or antifreeze with a vapor pressure of 3.75 milligrams of mercury and water having a vapor pressure of 17.5 millimeters of mercury at room temperature, or 20 degrees Celsius in our case, which has the higher boiling point? The antifreeze has the higher boiling point because it's got a lower vapor pressure at 20 degrees. And that will scale proportionately all the way to the boiling point. It turns out ethylene glycol has a decently higher boiling point than water, and it's because its intermolecular attractions are higher. In the case of ethylene glycol, it does have multiple spots to put hydrogen bonds, so it would be higher than the water, and you can tell that by the vapor pressure. Phase diagrams just show what's a solid, what's a liquid, what's a gas at a given temperature and pressure. And it'll be a little graph. At the interfaces, both phases can coexist, or all 3 phases in the case of the triple point. At the triple point, all 3 phases exist in an equilibrium. The critical point is the temperature above which you can't pressurize it to force it to be a liquid anymore. You can force certain, say, fuel gases like propane to be a liquid at room temperature. That's not normally the case, but above a certain temperature, that's not going to happen. And that's the critical point. Here are the phase diagrams of water and carbon dioxide. We can see solid, liquid, gas in those ranges, solid, liquid, gas. Water's a little bit unique. The solid liquid line angles backward, where it typically angles slightly forward, but you're going to get melting across here, boiling across here, sublimation across here. For water, we're talking about crossing the solid liquid line, then the liquid gas line. For something dry ice, the sublimation is going to occur because 1 atm is down here. This point in the middle is your triple point. Solid, liquid, gas all coexist equally. That may be difficult to achieve outside of the lab for some substances, and this is the critical point. And you can see those same points on the other graph. So if we want to Label each section. The liquid phase is in the middle, so that's point D. The solid phase is there to the left, so that's going to be E. The gas is in that rightmost section, so that's A. The triple point's that point in the middle, that's point C. The critical point's that point labeled with the arrow, and so that's point B. And so that would be how to do a phase diagram. We got viscosity. That's just how quickly something will flow. A lot of times we talk about oil in that range, 10W30 or 5W30, talks about the thickness of the oil. If you ever heard the expression that they move as slow as molasses in January, it's because molasses, when it's cold, has a very high viscosity and doesn't flow very well. It's hard to pour it. But again, that goes up as a function of intermolecular attraction. Something with a high rate of intermolecular attractions will flow more slowly. And things will flow more quickly at a higher temperature, more slowly at a lower temperature. Surface tension is the measure of the unequal attractions that occur at the surface. And water has a very high surface tension. That's why you see people jump in and try to minimize the surface. Nobody wants to do a belly buster into the pool. It hurts. You see the special forces guys jump out of the helicopter feet first. They're minimizing the area and try to break the surface of the water. A lot of times they say it's like hitting concrete if you do it from a distance. It's not really that, but you are going to smack and then the water is going to give. So it's not like concrete, but you probably don't want to hit it from any reasonable height. Or at least you want to minimize your surface area. But again, that property goes up with intermolecular attractions. Capillary action refers to going up a capillary tube. You have to compare the cohesive forces to the adhesive forces. The cohesive forces hold the liquids together. The adhesive forces are what makes it stick to the tube or the container. Capillary rise means the adhesive is bigger than the cohesive, and you get a capillary rise. The fall means the cohesive is greater than the adhesive. Obviously, the rise is going to be more favorable if the cohesive forces are bigger, which is going to go up with intermolecular attractions. Evaporation, just how fast it escapes from the surface of a liquid to become a gas. Evaporation is temperature dependent. Rate of evaporation will go up with temperature, but it will go down if the intermolecular attractions are bigger. A lot of times we talk about quickly evaporating liquids like, say, gasoline as volatile. A lot of times we translate volatile as flammable. No, volatile really means they evaporate quickly. Last but certainly not least, we'll talk about the distillation. Distillation is a process in which a mixture is separated based on a difference in boiling point. And it's another vapor pressure phenomenon, but if you were distilling a liquid in the flask here, you're going to heat that. It's going to go up the tube, and then there's a condenser that forces those vapors to condense and then drop in another tube. Usually need about a 20-degree difference in the boiling point for that to be reasonably effective. Certainly, the farther away they are, the better it works. Ideally, the substance with the higher boiling point is going to stay in the flask. The substance with the lower boiling point will go through the condenser to the Erlenmeyer.